You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Re-rankers are specialized models that operate after an initial retrieval step, taking a set of candidate results and reordering them according to deeper relevance analysis. The purpose of a re-ranker is not to perform the broad search itself that is left to fast approximate methods such as lexical or dense retrieval, but to refine the results to ensure that the most relevant, useful, and precise matches are surfaced first. In a sense, re-rankers act like quality control inspectors in a production line. The early retrieval system quickly gathers promising candidates, and then the re-ranker carefully inspects and prioritizes them. By narrowing focus to a relatively small number of candidates, re-rankers can apply more computationally expensive models without overwhelming the system. The outcome is a ranking that better reflects the user's true intent, often leading to large improvements in user satisfaction and task success. This leads to the familiar two-stage retrieval architecture, a design pattern seen across search and retrieval augmented generation RAG systems. In the first stage, a retrieval system quickly identifies hundreds or thousands of potentially relevant candidates. This stage must prioritize recall, ensuring that relevant items are included in the pool, even if some noise is admitted. The second stage, re-ranking, focuses on precision. Here, a more expensive but accurate model reorders the candidates so that the most relevant appear at the top. The pipeline reflects a division of labor. Stage 1 is about breadth, Stage 2 about refinement. This architecture balances efficiency and accuracy, enabling retrieval systems to scale to massive corpora while still delivering precise, high-quality results. Understanding re-rankers requires contrasting biencoders and cross-encoders, the two primary architectures in neural retrieval. Biencoders separately encode queries and documents into vectors, enabling fast similarity computation through vector dot products or cosine similarity. Cross-encoders, in contrast, jointly process a query and a candidate document in a single forward pass of the model, allowing richer interaction between the two. While biencoders excel at efficiency, cross-encoders deliver accuracy by modeling nuanced relationships directly. Re-rankers often adopt the cross-encoder approach, since they operate on a reduced set of candidates where the computational overhead is manageable. This distinction is central. Biencoders generate candidates quickly, while cross-encoders refine them with depth. The cross-encoder concept exemplifies the strengths of re-rankers. By feeding both the query and a candidate passage into the model simultaneously, cross-encoders allow token-level attention across both sequences. This means the model can evaluate how specific words in the query align with words in the document, capturing subtle matches and contextual relationships. For example, a query asking which drug reduces cholesterol can be distinguished from which foods reduce cholesterol, even if both candidate documents contain the phrase reduce cholesterol. A cross-encoder detects whether the context matches the intent, avoiding the false positives that a biencodер might allow. This joint evaluation makes cross-encoders state-of-the-art in re-ranking, particularly in question answering, legal retrieval, and other domains where precision matters. The benefits of cross-encoders are clear. They capture relationships that embedding-only approaches miss. Cross-encoders understand word order, phrase structure, and context at a finer granularity, enabling them to discriminate between superficially similar candidates. They can downrank passages that contain the right keywords but use them in irrelevant contexts, while upranking those that address the query directly. This leads to large improvements in evaluation metrics such as NDCG and mean reciprocal rank. In competitive benchmarks, re-rankers with cross-encoders consistently outperform biencoded retrieval alone. Their ability to refine results so effectively explains why they are central to the second stage of retrieval pipelines. However, these benefits come with latency costs. Cross-encoders must evaluate each candidate query document pair independently, which is computationally expensive. If 1,000 candidates are retrieved, a cross-encoder must perform 1,000 forward passes, creating delays that may be unacceptable in real-time systems. This computational burden restricts their deployment in scenarios where responsiveness is critical, such as conversational assistance. As a result, organizations often face trade-offs. Fewer candidates are re-ranked to reduce latency, or lighter re-rankers are used that approximate cross-encoder accuracy at lower cost. Latency remains the main constraint on cross-encoder use, forcing engineers to balance precision against speed. To mitigate latency, re-rankers are often distilled into smaller, faster models. Distillation involves training a lightweight student model to approximate the judgments of a large, accurate teacher cross-encoder. The student cannot fully replicate the teacher's quality but retains much of its performance while operating at lower cost. This allows re-ranking to be applied more broadly, even in resource-constrained environments. Distilled re-rankers exemplify the broader trend in AI toward efficiency without sacrificing quality. Powerful models set the standard, and streamlined versions bring them into production. In re-ranking, distillation ensures that high-accuracy models are not limited to offline or research contexts but can contribute in real-world systems. In practice, re-rankers are applied when precision matters more than speed. For example, in legal search, where missing a relevant case could have serious consequences, re-rankers ensure that the most relevant cases appear first. In e-discovery, medical literature search, or academic research, re-rankers provide confidence that retrieved documents are not just topically similar but directly relevant. They are also used in web search engines, where billions of queries must be served daily, though often with lighter or heavily optimized re-rankers to meet latency requirements. The unifying principle is that re-rankers step in when accuracy is paramount, even if it means sacrificing some efficiency. The latency versus accuracy trade-off defines the role of re-rankers in retrieval pipelines. On one side is speed, fast systems that return results instantly, even if some are irrelevant. On the other is precision, slower systems that guarantee the top results are truly the best. Re-rankers sit between these extremes, offering a configurable middle ground. Engineers must decide how much latency can be tolerated in exchange for improved ranking quality. This decision depends on context. In consumer search, users expect sub-second responses, while in professional research, users may accept slight delays for higher precision. Re-rankers embody this tension, delivering value where accuracy cannot be compromised but speed must still be acceptable. Evaluating re-ranker performance requires specialized metrics that reflect ranking quality. Normalized Discounted Cumulative Gain (NDCG) measures how well relevant documents are ranked near the top of results, emphasizing early precision. Mean Reciprocal Rank (MRR) evaluates the position of the first relevant document, rewarding systems that bring correct answers forward. These metrics reveal the practical benefits of re-rankers, showing not only that relevant documents are retrieved, but that they appear early enough to be useful. Without re-rankers, relevant items may languish deep in the ranking, effectively invisible to users. Metrics like NDCG and MRR demonstrate the tangible improvements re-rankers bring to retrieval pipelines. The resource requirements of re-rankers reflect their complexity. They consume more compute and memory than lightweight retrieval methods, since each candidate must be evaluated with a neural model. Scaling re-rankers to billions of queries requires optimized infrastructure, GPUs or TPUs, and careful engineering. These costs make re-rankers more challenging to deploy than simple retrieval systems, but their accuracy gains often justify the investment. Organizations frequently deploy re-rankers selectively, applying them only to queries or contexts where precision is critical. In this way, resources are allocated where they provide the most value, balancing cost against quality. Examples of re-rankers in industry are plentiful. Web search engines apply re-rankers to reorder results initially retrieved by keyword or dense search, ensuring users see the most relevant links first. E-commerce platforms use re-rankers to refine product search, surfacing items that match not only keywords but user intent. Enterprise knowledge bases rely on re-rankers to deliver precise answers from internal documentation, avoiding noise that frustrates employees. These examples demonstrate that re-rankers are not experimental features but operational necessities in modern search. They have moved from research labs into production environments at massive scale, shaping the daily experience of billions of users. In retrieval-augmented generation, re-rankers improve the quality of retrieved context that feeds into large language models. Without re-ranking, irrelevant or tangential chunks may dominate the context window, degrading output quality. By prioritizing the most relevant passages, re-rankers ensure that the generator is grounded in accurate, meaningful evidence. This reduces hallucinations, increases factual reliability, and improves coherence. RAG systems that include re-rankers consistently outperform those that rely on raw retrieval alone, demonstrating their critical role in generative pipelines. Re-rankers thus enhance not only search but also the next generation of AI systems built on retrieval-augmented frameworks. Open-source availability has made re-rankers more accessible than ever. Pre-trained cross-encoder models are available through libraries such as Hugging Face, covering domains from general web text to biomedical literature. These models can be fine-tuned on domain-specific data to improve relevance for specialized tasks. Open-source access lowers the barrier to experimentation, allowing organizations to integrate re-rankers without starting from scratch. It also fosters innovation, as researchers and practitioners build upon shared models to refine and extend re-ranking capabilities. This ecosystem has helped move re-rankers from niche research into mainstream deployment, supported by collaborative development across the AI community. Finally, re-rankers complement freshness strategies in retrieval pipelines. Even if indexes are up to date, initial retrieval may surface older but semantically strong matches. Re-rankers can incorporate temporal signals, ensuring that the freshest relevant results are prioritized. For example, in news search, re-rankers elevate recent articles over outdated ones, balancing semantic relevance with timeliness. In enterprise settings, re-rankers can downrank obsolete policies while highlighting current documentation. This shows that re-rankers are not only about semantic accuracy, but also about prioritization in line with user needs. They ensure that relevance is multidimensional, accounting for both meaning and context, such as recency. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Multi-stage retrieval pipelines demonstrate how re-ranking can be layered for progressive refinement. Instead of a single re-ranker, systems may apply multiple stages, each using increasingly sophisticated models. The first stage might involve a lightweight re-ranker that quickly prunes hundreds of candidates down to a few dozen, prioritizing speed. A second stage might use a cross-encoder to evaluate those remaining candidates with far greater depth, ensuring maximum precision. This staged design mirrors the way hiring works. An HR system may screen resumes automatically before handing a shortlist to human recruiters for in-depth review. By cascading re-rankers, systems achieve a balance between throughput and quality, applying heavy computation only where it matters most. Such pipelines are common in large-scale search engines, where efficiency and precision must coexist at massive scale. Hybrid re-ranking extends the concept by integrating lexical, dense, and metadata signals within one scoring process. While hybrid search combines lexical and dense retrieval at the candidate generation stage, hybrid re-ranking ensures those signals remain active during reordering. For example, a candidate document might receive a base lexical score for keyword overlap, a semantic score from embeddings, and a metadata score from structured attributes, such as publication date or source. The re-ranker fuses these signals, often using machine learning models to learn optimal weightings. This holistic approach reduces the risk of bias from any single signal, creating rankings that are robust across query types. In enterprise systems, hybrid re-rankers are especially valuable because they enforce metadata-based compliance while preserving semantic flexibility. They are effectively the referees that adjudicate across different evidence sources. Learning to rank methods, such as lambda-mart, paved the way for modern neural re-rankers. Before deep learning, these classical algorithms were widely used in search engines to combine multiple ranking signals into a single score. They relied on hand-engineered features like keyword overlap, click-through rates, or link authority. Neural re-rankers have now surpassed them by leveraging large, pre-trained language models, but the influence remains. Many re-ranker training processes borrow ideas from learning to rank, framing the problem as one of relative preference. Given a query and two documents, which should rank higher? Neural models operationalize this with deeper contextual understanding, but the core idea, training models to order candidates by relevance, is inherited directly from these classical methods. This continuity highlights how re-rankers represent an evolution of long-standing retrieval ideas, rather than a complete departure. Training data is critical for re-rankers, as they require labeled pairs of queries and relevant documents. Unlike dense retrievers, which can be trained on large amounts of unlabeled text via contrastive methods, re-rankers depend heavily on curated judgments. For example, datasets like MS Marco provide human-labeled query document pairs where assessors determine which passages answer the query. The model learns to score relevant documents higher and irrelevant ones lower. High-quality training data ensures re-rankers capture subtle distinctions, but it is also costly to obtain. Biases in labeling, such as overrepresenting certain topics, can skew performance. As a result, re-rankers often blend human labels with implicit signals like user clicks, balancing quality against scale. The training pipeline is resource-intensive but vital, since re-rankers' performance hinges on how well their training data reflects real-world query intent. Bias in re-ranking is a serious concern. Because re-rankers amplify the signals they are trained on, any bias in the data can become magnified. If training data overrepresents popular sources, re-rankers may consistently favor mainstream content while downranking niche but relevant materials. Similarly, if annotators carry unconscious stereotypes, re-rankers may learn to reflect them. This is especially problematic in sensitive domains like hiring, healthcare, or law, where biased rankings can have tangible negative impacts. Addressing bias requires careful curation of training data, fairness-aware objectives, and ongoing monitoring in production. The risk is not only technical but ethical. Re-rankers hold significant influence over what information surfaces first, shaping user perception and decision-making. Recognizing and mitigating these biases is therefore central to responsible deployment. Efficiency improvements have become a focus of re-ranker research, aiming to reduce latency while preserving accuracy. Approximate cross-encoders, for example, simplify architectures to lower computational load. Distillation, as discussed earlier, produces smaller models that approximate larger cross-encoders. Researchers are also exploring hybrid scoring pipelines, where cross-encoders evaluate only the most promising candidates identified by lighter re-rankers. Advances in model quantization and pruning also reduce the compute requirements of re-rankers, making them deployable in environments where hardware resources are limited. Efficiency innovations reflect the practical reality that re-rankers, while powerful, cannot succeed in production unless they meet strict performance constraints. The future of re-ranking lies in these compromises. How to deliver near cross-encoder quality without paying the full latency cost. Caching and pre-computation strategies provide additional ways to manage latency. Frequently asked queries such as weather in New York or latest quarterly earnings report can be cached with their re-ranked results. When such queries are repeated, the system can return cached results instantly, bypassing re-ranker computation. Similarly, pre-computing document embeddings or partial re-ranker scores reduces real-time work. While caching does not eliminate the need for re-rankers, since many queries are unique, it dramatically improves efficiency for common cases. This strategy mirrors real-world operations like customer service. Common questions have ready-made answers, while rare or complex ones demand more detailed attention. By caching predictable workloads, re-rankers can focus resources where they are most needed. Evaluation benchmarks play a central role in measuring re-ranker performance. Standard datasets such as MS-MARCO, BEIR, and TREC provide thousands of queries with relevance labels, allowing comparison across models and techniques. Metrics such as NDCG and MRR, introduced in Part 1, quantify ranking quality, while recall and precision provide additional perspectives. These benchmarks have become competitive arenas where re-ranker architectures are tested, refined, and validated. They also reveal trade-offs. Some re-rankers excel at factual precision, while others shine in broader coverage. Benchmarking ensures that re-rankers are not only effective in theory, but validated against real-world relevance judgments. Without such evaluation, it would be impossible to determine whether latency sacrifices are justified by meaningful gains in accuracy. Conversational AI applications benefit enormously from re-rankers. Chatbots and digital assistants rely on context retrieval to ground their answers, and irrelevant passages can derail dialogue quality. Re-rankers ensure that the most relevant conversational context is passed into the model, producing answers that are more coherent and contextually aware. For example, in a customer support chatbot, re-rankers prioritize documents directly related to a user's reported error rather than loosely related FAQs. This reduces hallucination and increases user satisfaction. In conversational AI, the re-ranker functions as a silent but essential partner, shaping the quality of dialogue by curating the knowledge fed into the system. Without re-ranking, generative dialogue systems risk being overwhelmed by noisy or tangential context. Re-rankers are especially valuable in legal and medical domains, where stakes are high and errors carry serious consequences. In legal research, retrieving relevant case law requires more than matching keywords. Subtle reasoning and context must be considered. Re-rankers help ensure that the most legally relevant precedents rise to the top, supporting accurate arguments. In medicine, re-rankers ensure that clinical queries retrieve passages aligned with evidence-based practice rather than tangential studies. This improves trust and reduces risk, since the cost of irrelevant or misleading information is high. In these domains, re-rankers are less about convenience and more about ensuring professional standards, safety, and compliance. Their role in refining retrieval underlines their necessity in specialized, high-stakes fields. Security and privacy considerations extend into re-ranking as well. Re-rankers must respect access controls, ensuring that restricted documents are not surfaced to unauthorized users simply because they score highly on relevance. In enterprise systems, this requires integration with authentication and authorization pipelines. Compliance frameworks such as HIPAA or GDPR add further requirements, ensuring sensitive data is not inadvertently exposed through re-ranking. Privacy concerns also arise in the training phase, where re-rankers may learn from user logs that contain sensitive queries. Anonymization and strict data governance are therefore essential. Re-rankers sit at the intersection of semantics and compliance, making their secure design as important as their technical performance. Latency thresholds for production deployment set hard limits on re-ranker use. Enterprises often require end-to-end query responses within strict bounds, such as under 200 milliseconds for web search or under 1 second for enterprise chatbots. Re-rankers that exceed these thresholds cannot be deployed, no matter how accurate they are. This forces trade-offs. Fewer candidates are re-ranked, lighter models are used, or re-rankers are applied selectively to high-priority queries. In some cases, re-rankers are deployed only in offline pipelines for analytics or evaluation, rather than in live systems. Latency thresholds highlight that re-rankers, while powerful, must prove their worth in real-world conditions, where user patience and operational budgets impose firm constraints. Emerging trends in re-ranking point toward greater integration of multimodal signals and personalization. Multimodal re-rankers evaluate not only text but also images, audio, or structured data alongside queries. For example, an e-commerce query might combine a text description with an uploaded photo, requiring re-rankers that can integrate both modalities. Personalization is another frontier. Re-rankers can adjust rankings based on user profiles, preferences, or history, ensuring results are tailored. These advances expand re-rankers' relevance, making them central not only in text-heavy search but across diverse data types and user contexts. They also raise new challenges in fairness and transparency, since personalized re-ranking can shape individual experiences in opaque ways. Looking to the future, re-rankers are expected to remain a cornerstone of retrieval pipelines, balancing efficiency and precision. They will continue to evolve, becoming faster, lighter, and more adaptive, but their role as the precision layer will endure. As RAG pipelines proliferate and context windows expand, the demand for high-quality retrieval will only grow. Re-rankers will ensure that the right information enters these windows, preventing noise from overwhelming generative models. Whether through distillation, multimodal integration, or personalization, re-rankers will adapt to the evolving landscape while maintaining their essential role. They exemplify the principle that retrieval is not only about finding information, but about ranking it effectively. Finally, re-rankers bridge into the topic of freshness and incremental indexing, the focus of the next episode. While re-rankers refine the quality of candidate sets, freshness strategies ensure that those candidate sets contain the most up-to-date information. Together, they form complementary aspects of retrieval quality. Re-rankers prioritize the most relevant matches, while freshness ensures those matches are current. This combination reflects the dual mandate of modern search systems, not only to be accurate, but also to be timely. Understanding freshness is the next step in appreciating how retrieval systems remain responsive in fast-changing domains. In conclusion, re-rankers refine retrieval pipelines by applying deeper models that reorder candidates with precision. They operate within multi-stage architectures, balancing efficiency and accuracy. Their power lies in cross-encoders' ability to capture subtle relationships, though latency remains their main constraint. Distillation, caching, and approximate methods mitigate costs, enabling broader deployment. Re-rankers are indispensable in high-stakes fields like law and medicine, as well as in conversational AI, web search, and e-commerce. They must be evaluated rigorously, designed securely, and deployed within strict latency thresholds. Emerging trends expand their scope into multimodal and personalized domains. As retrieval pipelines evolve, re-rankers will remain essential, ensuring that results are not only relevant but ranked with the precision users demand. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.